Hello and welcome to the final section of our mechanics module, which is going to be projectile and satellite motion. Projectile motion is the movement of an object through the air when acted upon by gravity. What will end up happening is illustrated in this diagram where for the X motion or motion parallel to the floor, no acceleration is being felt in the X direction or parallel to the floor. All the acceleration is in the Y direction. So whatever initial velocity you start out with in the X direction is going to be the velocity that you keep going in the X direction. Looking at these balls on the leftmost side, you will see that each ball for, say, 1 second apart is going to cover the same amount of distance because it has the same amount of velocity in the x direction or parallel to the floor. However, if you have vertical motion with only gravity and no horizontal motion, we've already seen that that will accelerate towards the floor and gain more velocity, meaning that it's going to start out not going very fast in the vertical direction, but then as time goes by, it's going to cover more and more space. When you combine these two ideals, as you see in the third and fourth images, what you end up having is the x motion is going to be at a constant velocity in the horizontal direction, while the y motion or the vertical motion is going to be accelerating down, which is going to cause there to be a shape called a parabola, which is going to be true of any object moving through a constant gravitational field. So where G is close to the Earth enough to basically be constant, it's going to move in a parabola. If you go into space, it is also going to move in a parabola as you go to Mars or the Moon, but it's going to have different properties depending on the strength of the gravitational field on Mars or the Moon or whatever planets or space station you're looking at. Another way that we can think about this is looking at this diagram where we have an initial path that a cannonball would take if there were no acceleration in the y direction, in which case it would just go in a straight line along the dashed path with no forces acting on it. However, because there is a force due to gravity, it is going to fall from that line by a distance equal to the amount that an object would fall in free fall if it were just let go. So there's a distance of 5 meters after 1 second between the dash line and the actual path of the parabola. And then there's a distance of 20 meters after 2 seconds and a 45 meters after 3 seconds. Further illustrating the point, if we break down the velocity vectors into x and y components, meaning a horizontal component showing what the velocity is in the horizontal direction, and a vertical component showing what the velocity is in the vertical direction, then as we go about our path, the vertical velocity is going to get slower and slower as it reaches the top of the path until it reaches zero vertical velocity. There's no vertical component of the vector at the top of the path. You will see that the vector is pointing entirely in the x direction, and then it is going to start going faster and faster as it is sped down towards the Earth. Whereas Whereas the horizontal velocity is going to remain constant the entire time because there is no force acting in the horizontal direction. Therefore, there is no acceleration in the horizontal direction. Because of these factors, we're going to see this parabolic motion, and that is going to be true as long as we have that constant gravitational field, as long as it doesn't go high enough up to cause the little g to change very much. We're going to have this parabolic motion that we see as we shoot a missile or shoot a rocket or shoot a cannonball or throw a football or anything that involves the object flying through the sky with only the force of gravity pulling down on it. That said, the angle does change the range, which is how far an object will go before it hits the ground again. This is going to be maximized for a 45-degree angle, as you can see in the diagram, for the different launch angles and their projectile motion. What is also cool about this is that for every degree that you go above or below 45 degrees, then you're going to end up in the same place. A launch angle of 30 degrees and a launch angle of 60 degrees with the same initial velocity will have the 30-degree angle one coming to the ground very fast, but because it has a lot of initial velocity in that direction, because 30 degrees is pretty low down close to the Earth, it is going to go as far as a projectile which is launched higher up at a higher angle of 60 degrees. The time that you're in the air is going to be higher for 60 degrees than 30 degrees because you're pointing your cannon up and you have a greater initial y velocity or vertical velocity. But as you go through the air, as that projectile goes through the air, it doesn't have as much of a horizontal velocity or x velocity, which means that it is going to just cover the same amount of distance, even in a greater amount of time. So it is going to land in the same position as 30 degrees. This is also true for 45 degrees plus 30 degrees or minus 30 degrees, which corresponds to the 15 degrees and 75 degrees, or any angle that you choose. Satellite motion is similar to projectile motion in that it is what happens when an object is far enough away that as it falls, it is going to orbit the planet or the moon or whatever you're looking at by constantly falling towards the planet, but not falling quickly enough to run into the planet. The way we realize this is that, as you see on the left, if you just push a rocket straight up, it is eventually going to fall down. But you wait until it's high up enough, you can give it a little boost of velocity and cause it to circle the planet instead of going straight in. Going back a little, we're going to look at Johann Kepler and Kepler's three laws, which don't really explain why something is happening and are thus not a great scientific theory. But what they observed happening and what they were able to predict would happen was used by Newton in order to come up with his laws of motion and his laws of universal gravitation. An ellipse is basically just a squashed circle, which is defined by the presence of two foci, where these are 2 points on the inside of the ellipse, where if you go at any point on the edge of the ellipse and draw a line to one focus and draw a line to the other focus, the total length of those two lines is going to be constant for any point along the ellipse. A circle is a special type of ellipse where the two foci converge on one single point so that when you look at the distance from the circle to that focus, it is going to constantly be the same amount. You don't have to worry about two lines being drawn, you just have to worry about one line being drawn to the center of the circle, which is going to be the focus. It is also true that the Earth and the Moon both largely follow circular paths, but they are slightly eccentric, which means that they are slightly swashed out and have the sun at one focus. The line from the sun to any The second rule is that the line from the sun to any planet sweeps out equal areas of space in equal time intervals. This is a consequence of angular momentum, and I'll talk about it more at length in the coming slides. And then the third law is that the square of the orbital period of a planet is directly proportional to the cube of the average distance of the planet from the sun. So the period squared is proportional to the radius squared for all planets. This is interesting and is physically important for how Newton was able to come up with the laws of motion and the laws of universal gravitation. But for the purposes of this class, this is not the most interesting thing. It basically just says that the year squared for any satellite or planet is going to be proportional to the distance away cubed for that planet. Here we see a good illustration of Kepler's first and here we see a good illustration of Kepler's first and second law, which is that any orbit that a planet makes around the sun is going to be an ellipse with the sun at one focus of the ellipse. So the sun is noted by the letter S in this, and it is one focus of an ellipse. As I said, a lot of planets and moons are closer to circles than ellipses, but an ellipse is just a more general version of a circle. The illustration of Kepler's second law here is that as the planet goes on its path, as the planet goes from A to B over the course of, let's say, a week, then the area of that grayed out triangle is going to be the same as when the planet goes from D to C over the same amount of time, let's again say a week. And why this is because the farther away you are from the sun, the slower you are going. So while the distance between points A and B is not very big, it does create a big triangle as it is farther away. And the distance between C and D is pretty big because it's closer. It creates the same size of triangle even because it is closer. And the distance between point C or D and the sun is not going to be as big. This is due to angular momentum. So if you'll remember, angular momentum is a measurement of how hard it is to stop something spinning in the same way that linear momentum is a measurement of how hard it is to stop something from moving in a linear motion. The reason that this is useful for us is because it is a conserved quantity so long as there's no torque. And as I said in the last lecture, when you have a gravitational force, there's not going to be any torque acting on the object because the force is directed directly along the arm of rotation. It's directed directly between the Earth and the Sun or the Moon and the Earth. Therefore, it can't cause any torque. As angular momentum is described by the angular inertia, I, times the rotational speed, omega. So if there are no changes in angular momentum, as a mass gets farther away, its inertia, as a mass gets farther away, the rotational inertia goes up, which, if there is no torque and no change in angular momentum, means that the speed that it's going to be going, the angular speed that it's going to be rotating at, is going to go down, causing it to go slower. And if you get and if you bring the mass in closer, then the rotational speed is going to increase, going faster. So when we look at these, the farther out you are, the more rotational inertia you have, which means that your angular speed goes down. But the closer you are to the sun, the more the closer you are to the sun, the less rotational inertia you have, meaning that you go faster. And a consequence of the mathematics is that these triangles, or these time slices rather, are going to sweep out this constant area, even though the object is going much faster from D to C than it is from A to B. Our final word on mechanics is going to be about escape speed. Escape speed is the speed needed to never get pulled back by gravity. It comes when the kinetic energy initially is greater than the change in gravitational potential energy between you and an infinitely far distance away. I don't want to define what gravitational potential energy is for. I don't want to define what gravitational potential energy is for Newton's general force, because that ends up happening when we do the math is that the velocity needed to escape a planet or a sun or any other gravitational pull is going to be equal to the square root of 2 times the mass of that object that's trying to escape from. So the mass of the Earth or the mass of the sun times the gravitational constant, which we were talking about last lecture, divided by the distance between you and the center of mass of the object. On the right are some escape velocities for different celestial objects in the solar system, but another on the right are some escape velocities for different celestial objects in the solar system, but another consequence of this is that if the mass is large enough and the center from the distance of mass d is small enough, then you can have it so that there is some distance away from the mass at which even light is not able to escape. And this is called the Schwarzschild radius of a black hole, and is what actually defines a black hole having this radius.